Assalamu alaikum and welcome to Mathcast with Faria Yusuf. And this video is the fourth lesson on differentiation, and we shall be doing stationary points and second derivative here. Stationary points. Any point on the curve where our dy by dx, meaning the gradient value, we know that this dy by dx actually means it's the gradient value here. Dy by dx, it's the gradient value. So when this dy by dx or the gradient equals a 0, then this point is called a stationary point. And we know that the gradient becomes a 0, that the gradient equals to 0 when a line is a horizontal line. We know that a gradient is 0 when the line is a horizontal line or it is a horizontal. So let's discuss some cases for stationary points. Number 1, if a curve is given, it's a quadratic curve. We can see it's a quadratic curve with a minimum turning point here. This minimum turning point, at this point, if I make a tangent at this turning point, if I make a tangent, then I can see that this tangent is a horizontal at this point P. The tangent is a horizontal, and at this point, this dy by dx becomes a 0. So this point is called the stationary point, and it is the minimum point on the curve. In the same manner, if I have the curve with a maximum turning point, this is our maximum turning point, and if we have the tangent here passing through this point, then here this point becomes the stationary point, this point here where the tangent becomes horizontal or parallel to the x-axis, or the over here the gradient then becomes a 0, and this point is then called the stationary point, and we can see that the nature for this stationary point is a maximum. Thirdly, if I come to the cubic equation, if this is the cubic equation, so I know it's a cubic equation because the cubic equation follows two stationary points, and this is the condition where we say that the coefficient of x cube, we know that it's the coefficient of x cube needs to be greater than 0, meaning it's a positive coefficient, then we shall be having the curve so that there are two turning points here. First, it's the maximum turning point, and then secondly, it's the minimum turning point. And then other thing that I see here is that at this turning point, if I make the tangent, then being horizontal, the gradient of the tangent here becomes a 0. In the same manner, at the minimum point, if I make the tangent, then at this point, tangent being a horizontal line, our gradient then becomes a 0. So at both of the points, maximum, minimum, the stationary points, the gradient then becomes a 0. So these two are known as the stationary points where the gradient becomes a 0. In the same manner, if we look at the second example or the curve that I have drawn here, I can see that here it's the minimum turning point and then we have the maximum turning point, and this is the case where the coefficient of x cube is less than 0. So first it is going to be the minimum turning point and then it's going to be the maximum turning point. These two turning points, they are the stationary points, minimum and maximum, and at both these points the gradient becomes a 0. And here again, as we have done increasing and decreasing functions in the previous video, so here if I just do the recap of all the four curves that I have drawn, I can see that in the first case, just before the turning point, if I draw tangent at any of these points on the curve, I can see that the tangent will be the line which will be sloping downwards. So this then is going to be a decreasing function. On this side, I can see that this is going to be a decreasing function. So before the turning point, I can see it's the decreasing function, and here I can see that my dy by dx has to be less than 0. Then it becomes a 0 at the stationary point, and after the stationary points I can see that the function is an increasing function. Therefore here the gradient becomes greater than 0. Over here this is going to be the increasing function. For the second case, I have the turning point here. I have this turning point here, and before the turning point I can see that the function is increasing. Here the function is increasing. Therefore this is the increasing function on this side. It's the increasing function on this side, and at all points on this side before the stationary point, the gradient value has to be greater than 0, meaning positive, and then at the stationary point the gradient becomes a 0, and after the stationary points again I can see that it is a decreasing function. It's a decreasing function, it's sloping down. So if this is a decreasing function, then here for decreasing function here we have the decreasing function, therefore our dy by dx shall be less than 0. So always before the stationary point and after the stationary point, the gradient changes its sign, as we have seen in both the cases. Now, if you look at the third case that I have drawn, I can see that I have the stationary point here, and just before the stationary point, it's increasing, then it's decreasing, then then at the stationary point again the gradient becomes a 0, and after that it becomes an increasing function. So here again I can see it's an increasing function here. It's an increasing function where the gradient dy by dx, it has to be greater than 0. Stationary point here the gradient becomes a 0. Then between the two stationary point, what I can see here is that it is a decreasing function where my dy by dx needs to be less than 0. So this was a decreasing function here. And then after this stationary point, again I can see that the function is increasing, and therefore here for the increasing function, the gradient needs to be greater than 0. So this is how the gradients change sign before and after the stationary point. Again, if we look at the last case, stationary point here, just before the stationary point, it's a decreasing function. I can see that the function values are decreasing. It's a decreasing function here. Therefore, for this decreasing function, our gradient dy by dx needs to be less than 0. Then the function has a stationary point where the gradient becomes a 0. And between the two stationary points, here between the two stationary points, I can see that the function is increasing here. So at this, between the two stationary points, the function is an increasing function, and here our gradient dy by dx needs to be greater than 0. And then after the stationary point here, again the function is decreasing. Therefore here it is a decreasing function, and on this side it's the gradient value which needs to be less than 0. So this is what happens when we have stationary points. So the concept must be clear that stationary point is the maximum or the minimum point at which the gradient of the point, the gradient at the point of the tangent becomes a 0, and just before and after the stationary point the gradient changes its sign, as we have discussed in the 4 cases. There are 3 types of stationary points. There are 3 types of stationary points. Number 1, maximum point, as we have discussed earlier. So maximum point, this was the curve. We have the stationary point here, which is a maximum at this point. This is my stationary point. Maximum here, my dy by dx for the tangent being horizontal becomes a 0. Second is the minimum point. Minimum point here, the curve is a minimum nature. Here again I can see that it's the dy by dx here, which at this stationary point becomes a 0. This is the stationary point and the tangent is horizontal, therefore the gradient is a 0. The third type is called the point of inflection. Now what we have discussed up till now is that the gradient was changing sign before and after the stationary points. Now, point of inflection, let's say we consider this curve here, this curve here. So what I can, this curve is basically, let's have an example. Let's say this curve is representing for y equals x cubed. So what we can see here is that the tangent becomes horizontal at this point. This is the stationary point. The tangent becomes horizontal here. Therefore, the gradient at this point becomes a zero. So just before the stationary point, what we observe is that the function is an increasing function. Here, the function is an increasing function. And then after the stationary point, the function is also increasing. So here what I observe is that on both the sides of the stationary point, the function is an increasing function. On both the sides, the function is an increasing function. So this point, the stationary point, is called the point of inflection. So point of inflection is the stationary point before and after which the gradient does not change its sign. And the second case that I have drawn here is this case, and this is the case for, let's say, I can just give an example as a negative x cube. So if this is a negative x cube, then this is the stationary point at which I can see that the gradient is a zero. And what I have observed, or what I can observe here, is that the function here is a decreasing function. It's going down, it's a decreasing function. And after the stationary point also, it is a decreasing function. So here I can see that the gradient dy by dx on both the sides of the stationary point, this is less than zero, it's a decreasing function here. And after the stationary point also, I can see that it is a decreasing function where my dy by dx is less than 0. So such points where before and after the stationary point, the gradient does not change its sign, they are called the point of inflection. So three types here, the maximum point, the minimum point, and then the point of inflection. Here it was the maximum stationary point. Here it's the minimum stationary point where the dy by dx, or the gradient, is a zero. Now the second thing that we need to discuss here is the second derivative. We have discussed the stationary points. Now the second derivative. So what is the second derivative? So second derivative, as the topic has suggested, that we shall be discussing the second derivative here. So what is a second derivative? Second derivative is that we have seen up till now that an equation is given for y in terms of x, for which we can have the first differential or first derivative dy by dx. We will be differentiating y with respect to x to get a dy by dx. So we know that dy by dx actually gives us the gradient equation for the curve. Now, if I need to derivate this first differential dy by dx, then this is called the second derivative, and we should be writing it as d2y, d2y, there is a 2 on d, y, and then it's dx square. So x has a square on it. So this is our second derivative, and this second derivative, it defines the nature of the stationary point. We have discussed the stationary points. We have seen what the stationary point is. It can be maximum, it can be minimum, or it can be the point of inflection where the gradient is a zero. Now, if a curve equation is given to us, so to identify the nature of that curve equation, we shall be going for the second derivative. So this is our second derivative, and this is the way to write the second derivative, d2y over dx square. Now, how to get the nature of the curve? If this second derivative, it comes out to be greater than 0, meaning if this is a positive, it's a positive value, the second derivative has a positive value, then in this case we say that the curve shall be having a minimum stationary point. It's a minimum natured curve there. if the second derivative is less than 0, which is a negative, then we should know that this shall be having a maximum stationary point. It has a maximum nature. And then if it comes out to be equal to 0, the second derivative, it comes out to be equal to 0, then the stationary point can neither be maximum nor minimum, and that this will be for the third case that we have seen earlier for the point of inflection here. So this is how we shall be solving or defining the nature of the curves with respect to the second derivative. So let's do an example to clarify the concept. Question 1. Find the coordinates of the stationary points of the curve y equals x to the power 1 by 2 times 3 by 4 minus x and determine their nature. So we can see that here in this question, two things are being asked. Number one, we need to find the coordinates of the stationary point. And secondly, they are asking for the nature also. They are asking us to determine the nature also. So as soon as we come across the word stationary point, we should know that here the question is asking about the point where the gradient value dy by dx shall be equal to 0. So if the question is given for y, which is equals to x to the power 1 by 2 times 3 by 4 and a negative x, then I should know that first I should be getting the first differential or the gradient equation here to get the stationary points. So first thing here is to solve or expand the equation. I can say this equation then can be written as 3 by 4 x to the power 1 by 2 minus x times x to the power 1 by 2. So x into x to the power 1 by 2, solving the indices, I can say it's a 3 by 4 x to the power 1 by 2 minus x to the power 1 plus 1 by 2, that shall give me a 3 by 2 here. So I have my y equation in terms of x. So here I can get the first differential, differentiating y with respect to x, it's dy by dx. And this then shall be 3 by 4 times the power, which is 1 by 2. And then x should be to the power 1 by 2 and a minus 1. And then for the second term, it's 1 times 3 by 2, giving us a 3 by 2, and x to the power 3 by 2 and a negative 1. So my first differential equation here in this case becomes 3 by 8 x to the power negative half and minus 3 by 2 and x to the power 1 by 2 here. So this is my first differential equation, and from here I should be getting my stationary point, because I know at the stationary point our dy by dx, the gradient value is a 0. So at stationary point, as discussed earlier, our gradient dy by dx, this shall be equal to 0. So I will be substituting 0, and then this is 3 by 8 under root x minus 3 by 2 under root x here. So I'm supposed to get the value of my x. Therefore, what I can do is I can say it's a 3 by 8 under root x, and I can take 3 by 2 under root x on the other side, so that this is what it becomes. And then I can see it's a 2 times 3, which shall be equal to 3 times 8 square root of x into square root of x. So the 3 here gets simplified. 2 divided by 8, that shall give me a 1 by 4, and square root of x into square root of x, that shall give me an x. So here I can say that my x value is equal to a 1 by 4. So this is the x coordinate where my dy by dx is a 0, and obviously then this is going to be the x coordinate of the stationary point here. Now stationary point, the coordinates of the stationary point, I shall be needing the y coordinate also. So for that I will substitute this x in the given equation, and the given equation had y, which was equal to So to get y, I should be substituting x equals 1 by 4 in the curve equation, and the curve equation was equal to x to the power 1 by 2 and 3 by 4 minus x. So if x is equals to 1 by 4, then I can say it's a 1 by 4 to the power 1 by 2 and 3 by 4 minus 1 by 4 here. 1 by 4 square root of 1 by 4, that shall be a 1 by 2, and here I will be left with a 2 by 4. The 2 here gets simplified and I'll be left with a 1 by 4 here, meaning the y coordinate with respect to x as a 1 by 4 is going to be a 1 by 4 again. Therefore, I can say that the stationary point has coordinates which are 1 by 4 and also a 1 by 4. So both the x and y coordinates in this case, they are going to be a 1 by 4 here. So the next step will be to find the nature of the stationary point. So after getting the stationary point, which in this case is 1 by 4 and a 1 by 4, x and y coordinates, they are both 1 by 4. The second thing that was asked in the question was to get the nature. Now, to get the nature, we know we have to go for the second derivative. We have found the first derivative, which was dy by dx, which is equals to 3 by 8 x to the power negative 1 by 2 minus 3 by 2 and x to the power half. This was the gradient equation. From the gradient equation, I will be getting the second derivative d2y over dx square. So this then shall be 3 by 8. I just need to differentiate the equation. So it's 3 by 8 times negative 1 by 2, and x needs to be 1 by 2 and a negative 1. And then I should be having a negative 3 by 2 into a 1 by 2, and x then shall be a 1 by 2 and a negative 1. So my second derivative here can be simplified to negative 3 divided by 16, x to the power negative 3 by 2 and negative 3 by 4 and x to the power negative 1 by 2. If I write it in more simplified form, then it's d2y over dx square, and this second derivative then shall be equal to a negative 3 by 16 x to the power 3 by 2 minus 3 by 4 and square root of x. Now we need to find the nature of the stationary point, and that is when my x, as we found earlier, for the stationary point, the x coordinate was a 1 by 4. So if I substitute this 1 by 4 here, then I can see that the second derivative d2y over dx square, this is going to be a negative 3 by 16 and 1 by 4 to the power 3 by 2 minus 3 by 4 and 1 by 4 to the power half. So solving it further, what I can see here is that even if I simplify this 1 by 4, there is one thing which is very much clear. Both the signs here, they are negative, and if I simplify both of them, my answer is going out to be a negative. So if this value comes out to be less than 0, what I have seen here is that my second derivative d2y over dx square is less than 0 when the stationary point was a 1 by 4 and a 1 by 4, and therefore I can say that this stationary point should be having a maximum nature, meaning it should be the maximum, it should be a maximum. In other words, we can say that this is actually the maximum turning point. So this is how the second derivative is helpful to identify the nature of the curve. So the second question that I have chosen is from October-November 2015, paper 1, variant 1. A curve has equation y equals 8 by x plus 2x. Part 1, find dy by dx and d2y over dx squared. So we need to find the first derivative, and then they are asking us to find the second derivative as well. So let's start solving this equation. Part 1, it says it's y, which is equals to, I'm writing it in a simplified form, which will be easier to find the first derivative. So y equals 8x to the power minus 1 plus 2x. So if I get the first derivative, then I can see here that dy by dx is going to be a negative 8 x to the power minus 1, and then it should be a plus 2 here. So further I can say it's dy by dx, which shall be equal to negative 8 x to the power negative 2 and a plus 2. So, or I can say it's dy by dx, which shall be equal to negative 8 over x square and a plus 2. So this is going to be the first derivative dy by dx. They have also asked us to get the second derivative, and for that I shall be using the first derivative equation, which is dy by dx, which was equal to negative 8 x to the power minus 2 and a plus 2. So differentiating this the second time to get the second derivative, it's d2y over dx square, which shall then be equal to minus 8 times minus 2 x to the power minus 2 minus 1, and the 2, the constant, it gets eliminated here. So solving it further, I should say it's the second derivative d2y over dx square, which then shall be equal to a 16 x to the power minus 3, or I can say it's a d2y over dx square, which then shall be equal to 16 divided by x cubed. So this is going to be the second derivative for this equation, and this is how I shall be solving for part 1 here. The second part of the question says, find the coordinates of the stationary point. Let's start underlining the keywords. They are asking for the stationary points and state with the reason the nature of each stationary point. So we know stationary point is when my dy by dx equals a 0. And then to get the nature, we have the three conditions for the second derivative: to be less than 0, greater than 0, or to be equal to 0. So first, let's start solving for the stationary point where we know that our dy by dx is equal to a 0. So second part, to get the stationary point, I know that my dy by dx is equal to 0. I have the first differential equation, which was negative 8 over x squared plus 2. Here, the first differential is a 0, so it's going to be negative 8 by x squared and a plus 2. I can bring the negative 8 by x squared on the other side, making it a positive, and then I can say that equals a 2. Solving it further, I can say it's x squared, which is equals to 8 divided by 2, which gives me a 4. X squared equals a 4, therefore I can say that it is the x, which can be equal to a positive and a negative 2 here. So here I can see that I am getting two values of x, two x coordinates. That means that there are going to be two stationary points for the given curve here. Now let's first find the y coordinate also. So to find the y coordinate, let's substitute this x in the given y equation. We have y, which is equal to 8 by x. This was given in the question. It was 8 by x plus 2x. So if our x is a positive 2, I will be getting the y, which shall be equal to 8 divided by 2 plus 2 times 2. And this then shall be equal to a 4 and a plus 4, or I can say it's y, which is equals to an 8. So I can have one of the stationary point, which is a 2 and a 4. For the second one, I can substitute x as -2, and in this case we'll say it's y, which is equals to 8 divided by -2 plus 2 times -2, or I can say it's y, which is equals to a -4 and a -4, and in this case our y is a -8, and it was an 8 here, and here I can see that the stationary points are -2 and a -8. So we have two stationary points here. The question was asking for the stationary points, and here the two stationary points are 2, 8 and a -2 and a -8, or I can also write this as a +-2 and a +-8 here. Now for the second part of the question, the second part was asking for the nature of each stationary point. So this is what they meant by each stationary point. There are more than one stationary points here. So to get the nature of the stationary points, I should be using the second derivative. And I can see that the second derivative that I have obtained is 16 over x cubed. So let's use the second derivative to get the nature. So to get the nature, I will be using the second derivative d2y over dx square, which we found to be 16 over x cubed. So in this second derivative equation, if I substitute x as a 2, I can see that the second derivative is a positive d2y over dx square. So this becomes a 16 divided by 2 cube, which is 16 divided by 8, or I can say it's the second derivative d2y over dx square, which is equals to a 2, and this 2 is greater than 0. So what I have seen here is that when my second derivative is greater than 0, this point 2 and +8, 2 and +8, they have to be of minimum nature. As they are greater than 0, simply I can say that therefore 2 and 8 will be of minimum nature. In the same manner, I will be substituting x as -2 in the equation, in the second derivative equation. So that would give me d2y over dx square, which shall be equal to 16 divided by -2 the whole cube. And here I should be having 16 divided by -8, or I can see that the second derivative here comes out to be a -2, which is less than 0. So as -2 is less than 0, therefore nature has to be maximum. Therefore, what I can see here is that -2 and a -8, -2 and a -8, this stationary point shall be of maximum nature. So this is how I will be identifying the nature of each stationary point here. So this is how useful the second derivative is to find the nature of the stationary points. So the next question related to the topic that I have chosen is from Winter 2016, Paper 1, Variant 2, and it's question number 7 in the paper. And the question says that the equation of a curve is y equals 2 plus 3 over 2x minus 1, and they are asking us to obtain an expression for dy by dx. So let's start solving from part 1. So for part 1, they have given us the curve equation, which is y, which is equals to 2 plus 3, and I'm writing this equation by taking the denominator to the numerator and having the outer power, which is a -1. So I have this equation. I need to have the first differential of y with respect to x, so dy by dx here. 2 is a constant, it gets eliminated. Second term, 3 gets multiplied by a -1. I can see that this is a composite function, so I should be solving it by the chain rule. 3 times -1, and then it should be 2x minus 1 to the power -1 and a -1. And in the second step, I shall be differentiating the function itself, which is 2x minus 1. So dy by dx here, in this case, the differential of y with respect to x shall be a negative 3 and 2x minus 1 to the power minus 1, that shall give me a negative 2. So I'll be writing it in the denominator with the power as a positive 2, and then it should get multiplied by the differential of 2x, giving me a 2. Negative 1 gets eliminated. So overall I can say that my first differential dy by dx shall be equal to a negative 6 divided by 2x minus 1 the whole square. So this is going to be the answer for this first differential dy by dx. Second part, explain why the curve has no stationary points. So no stationary points. So we know at the stationary point, my dy by dx, it should be equal to a 0. So let's equate dy by dx to 0. Explain why it has no stationary point. This is what the question asks. So if I equate my dy by dx to 0, dy by dx equals 0 at stationary points because the gradient is 0, the tangent is a horizontal. So if I equate it to 0, it's negative 6 divided by 2x minus 1 the whole square. And what I have seen here is that this 2x minus 1 the whole square, when get multiplied by this 0, it becomes a 0, and then this equation here is impossible to find the value of x. So simply I'm going to write that there is no stationary point. They are asking us why the curve has no stationary point. So I'm going to just write that this is impossible to solve for x. This is impossible to solve for x. Therefore, there is no stationary point. Now let's move to the third part of the question. The third part says, at the point P on the curve, now there is a point P on the curve where x is equal to a 2. So we have the curve equation, and on this curve equation, our x has a value which is a 2 here. So show that the normal to the curve at P passes through the origin. So this normal here passes through the origin, which means first I should be having the normal equation. So to get the normal equation, they have given us the x, which is a 2. And to have the normal equation, the things which I know or we should know are that it should be y minus y1, which is equals to the gradient of the normal times x minus x1. So I should be knowing y1, I should be knowing x1, and then I should be knowing the gradient of the normal. They have given us this x, which is a 2. So I can have this as my x1. To get y1, I will be substituting this x equals 2 in the curve equation. And then to get the normal, I will be using my differential equation here. So let's start working on it. So to start working on part 3, I have my x, which is equal to a 2. They have given us the point at P. My x is a 2, so I can very easily get the y coordinate by substituting this x in the equation, in the curve equation. And this y coordinate, the corresponding y coordinate, then becomes a 4 minus 1, or I can say it's a 2 plus 3 divided by 3, which gives me a 1. So I can say it's y, which is equals to 2 plus 1, or y is equals to 3. So that means the point P has coordinates which are 2 and 3. To get the normal equation, I will be now using the first differential equation, which was, so to get the gradient of the normal, I will be using the gradient equation, which was negative 6 over 2x minus 1 the whole square. So again, I know the x, it's a 2, so I can get the gradient of the tangent, which then is going to be negative 6 divided by 2 times 2 negative 1 the whole square, or I can say it's a negative 6 divided by 4 minus 1 the whole square, which shall give me a negative 6 over 4 minus 1, it's a 3, and 3 square shall give me a 9. Therefore, solving it, I can get the tangent equation, which is a negative 2 by 3. So if this is the equation of the tangent, then from here I can very easily get the equation of the normal, and I can say that the normal has the gradient, which is a 3 by 2 here. So this is the required gradient which I shall be using to have the normal equation. So I have x1, I have y1. I know that equation of the normal is y minus y1, which is equals to the gradient of the normal times x minus x1. So substituting this point P as 2 and 3 in the equation, I should say it's a y minus 3, which is equals to a 3 by 2, and x minus 2, or it is 2 times y minus 3, which is equals to 3 times x minus 2, or further I can solve it as a 2y minus 6, which is equals to a 3x and a minus 6 here. The negative 6 gets cancelled and I'll be left with 2y, which is equals to 3x. So this is going to be y is equals to 3 by 2x. This is going to be the equation of the normal. So this is now the question has said that we have to show that the normal passes through the origin. Normal at P, it passes through the origin. So if it passes through the origin, then it means that if my x is a 0, if my x is a 0, my y should also be a 0. So I can see in the equation that if my x becomes a 0, here if my x becomes a 0, the y also is becoming a 0. Therefore, I can simply say, therefore, the normal at P passes through the normal at P passes through the origin. And this is shown. So this is what the concept of stationary point and second derivative is. I hope it's clear now, and I shall be ending the video, and in the next video I shall be meeting you all with the topic of optimization. So best wishes, and let's meet you all in the next video. Thanks for watching, and Allah Hafiz.